will come up today, and I think we're ready to go. Are we ready to go, everybody? Folks are online, you can hear. Masha, is everything okay?
Yeah, I can hear. Yeah, good.
Thank you. You know, I am not monitoring the chat. Anish, if I can ask you a favor to just be on this and see if anything strange happens. Okay, so today is my favorite lecture, and I hope it comes to be one of your favorites. I hope it's not just completely confusing. I hope it's illuminating. We built up an apparatus for doing rotations. And this is the first actual problem, not student exercise, but actual problem that I'm going to use. And the problem is, in the initial step, what happens to the resonance frequency during magic angle spin? Like, give me the time dependence of the instantaneous frequency during magic angle spinning. And at the end of the lecture, if there's enough time, then I'll show you how you make a spectrum out of that. If there's not enough time, I'll do that tomorrow. But our immediate target is simply to write the frequency, instantaneous frequency of a general rank 2 interaction, CSA or dipolar, as a function of time because of magic angle spinning. Again, we can turn that into a spectrum, and if we need to do that at the beginning of Thursday or tomorrow, we'll do that, okay? This is the first real application of these rotations. So it has a few sections. This lecture has a few sections. The first one is the idea of nested rotation frames, what they're going to look like. And then some of that stuff is below there is what might get pushed to tomorrow. And at the end of this exercise, I think we'll have a good understanding what is so magic about the magic angle. What do we mean with that kind of hubris of calling it magic? The problem we're going to do is a uniaxial interaction initially. We pick a uniaxial interaction, such as we motivated the idea that dipole interactions were uniaxial last week, or some special CSAs. They're rare. Okay, so there are some functional groups that give uniaxial to a very good approximation. And that's the PAS having only one component of interest here. Only one component of interest. That is L equals 2, M equals 0, UDS. We're also only asking for the frequency measurement, the instantaneous frequency, and that is in the laboratory form. Defined by B naught, we have L equals 2, M equals 0. Only one spherical harmonic component in each frame. Only one calculation. This is what we did at the end of last time. That's the static experiment. The orientation-dependent frequency calculation. And we started with this big general expression that says I have various interactions C, and they have those constant. I mean, the name of the interaction is lambda, and it's constant with all the units in C. I might have L equals 0, 1, 2, but I can focus on what I really need. They're all real physical things, usually. Okay. And for each of those interactions, I will have spin and spatial terms. Spin in one nomenclature, which is used by Cease, for example, and some of Malcolm Levitt's works, T, the spin degrees of freedom, which we collected into a rank 2 tensor. We did a funny rearrangement of our spin degrees of freedom, and we re-represented them as a rank 2 tensor. That tensor will have a angular momentum quantum number and a component along Z. L and F are describing the molecule's environment, we'll have an L and M. What we need to do is match components. We're not getting anything other than zero. If you have a different L or a different M, match components, multiply. And the detail that we really dug in on is that our spin degrees of freedom are quite naturally written in the lab frame. I calculated them for you. We know what they are. But the problem is that the DAS is not the same as the lab. So our spatial degrees of freedom are naturally written in the DAS. So we said we need to rotate it. Rotation for the spherical harmonics, just like for the Cartesian, is a linear operation. So rotation is preserving a norm. It recombines linearly different components. And in particular, here's what it is. And we motivated this at length in the last lecture. So what's this is the rotation around Z. And that's the magic of spherical harmonics, is that they are eigen operators of the Z rotation. They make the Z rotation as dead easy as it could be. A phase factor and nothing more. So 2 Z operations in the tangle sandwich. It's the middle that you asked me a question about, Krishna. That is a rotation around Y. We do not represent rotations around X explicitly. The middle guy is a rotation around Y. This angle sandwich is completely general. You can do any rotation with those three, like the analogy I gave you about angles in directing an airplane. It's enough. 3 angles is enough. Now, this thing here is the mixing of the M components. So if you start with a pure M component, you leave it physically alone, nothing's changing for it, but you change your frame of reference, it will look as if what used to be a pure Z is now X and Y. What used to be a pure M equals 0 now has M equals 2, 1, minus 1, minus 2. Linear operation, which is a trigonometric function of that angle beta. We had the table, the lookup table. Okay, I'm just summarizing where we left off last week because it's been a few days. Now, I'm saying that for this particular problem, all we need is M equals 0. We got a big sum. It looks very fancy, but we only have one calculation we need to be doing. We're staying with L equals 2. That's the only thing that moves us from the isotropic shift. And both in the PAS and in the laboratory frame, we only need M equals 0. Everybody good? Yes, please, Krishna.
Yes, can we go back to the previous slide or from the PAS to the lab? So this question is also relevant to the problem that we are doing, problem 7. I am confused about representation of tensor in different axis system that we are considering. First, we have the Cartesian tensor. By that, we mean the tensor that's represented in this Cartesian system, X, Y, Z. We have these Cartesian spherical tensors.
Well, they're not Cartesian spherical. They're either Cartesian or spherical.
Oh, sorry,
Yeah.
spherical tensors.
Mm-hmm.
And that tensor we represent in the spherical harmonic basis sets using those basis sets. In that,
Right, and I showed you the decomposition. So you could take your Cartesian 3 by 3 and you could pull out with a overlap interval kind of thing. But you project the basis set for that value of L and M, and you pull a number because this is the dot product of 2 3 by 3 tensors. You pull out one number that says I'm the amplitude of that particular spherical harmonic. So you have 9 of those. You have 9 basis sets, you have 9 components that you pull out, L equals 0, 3 for L equals 1, and 5 for L equals 2. So you have these instead. You've thrown away your Cartesian, we don't need it anymore, and we have these amplitudes of the Cartesian basis.
okay. So I'm just trying to clarify in my head, in my brain, that we are talking about 4 different axis systems here. Whenever we are talking about tensor, because we have one PAS system, right? Where we
Right now we only have 2.
right now
For
we
this
only
one.
have 2, yes.
When we have 3, then we can talk about 3. And you'll be glad I don't do the problem with 4, even though it's a useful problem.
So when we are saying the transformation of tensor from PAS to the lab, we are saying that we are representing tensor in the PAS frame and then transforming it into the lab frame. Right now,
Well, yeah, we may know it in the PAS frame from a calculation, a paper. That's the way we share this. Can't share a lab frame with our friend David Case, but we can share the values in the PAS. So that's what we publish and that's what we get out of the literature. But then when we do our experiment, we have to say, oh, wait, my molecule's rotated. What's the frequency? How do I compute that? And with the Cartesian, you use those rotations that like looked a lot like high school geometry. We kind of walked our way through them. Here, we're thinking in a different way. We're saying, this is the M equals 0, L equals component is the only guy in town. Same thing in the laboratory frame. So I just need to ask how much of that projects onto that when I do a rotation. Linear operation. Trigonometry is not a linear function, but it's a linear operation overall. Rotation. Okay.
And if I could interject, we do this because of the convenience of this formula that has the capital D's. That's a very convenient transformation. But Ilya Kuprov's book Spin, Ilya hates spherical harmonics. So he represents everything in Cartesian frames from start to finish. So you can do it, but you then don't have this convenient formula there for transforming R from one frame to a different frame. You have something that's much more algebraically complicated. But Ilya can keep very complicated algebraic expressions in this frame, and I cannot.
Well, you see that in the homework, the difference in complexity. I mean, with just the one frame transformation, you might say they're competitive because one is more elegant and short, but attached to your brain more, and then the other one is tedious, but you do exactly what you were doing all. But as soon as you get to more rotations, like when you do with the MAS, there's no comparison. I think Leah's point is well taken that we're going to task a computer, not ourselves. I mean, you can type these all out and everything, but even there, I mean, an efficient code anticipates that some calculations are not needed. And that's exactly what the essence of this is. Anticipate in advance, certain things are not needed, let's not do them. Okay, so anyway, we were here, I was saying, these Y rotations, the projection of one of those L equals 2 components on the other, that's all we need for this problem. And moreover, we only need to project 0 on 0. We only need D super 2 sub 0, 0 for this problem. And so I give you a lookup table so you can find T20, I give you a lookup table, you can find R20. And then you could look up D200 of beta or little d out of the other lookup table I gave you, and it's one line and you're done. Put that together into an equation, it's at the bottom. So the instantaneous frequency is given there. Now, I just want to say already, that's a spectrum. That's a line shape. The most famous version of which is the so-called tape pattern. We alluded to it a couple of times. We start with that equation for the frequency, substituting for beta, a random number generator, generating a powder pattern. There's a famous paper by George Pake looking at high rates of gypsum, looking at hydrogen line. And this goes way back to 1948, so as old as NMR, it's really. And he asked the question, what's going to be the probability of each frequency? And so to do that, he says, well, what's the probability of each angle theta? And then what's the partial derivative of the frequency with respect to theta? And there's just one trick in this problem, which is that you have a singularity because you have a square root, and so you have to do it piecewise. But otherwise, it's a rather straightforward thing. You get a derivative of an arc cos, and you end up with a line shape that looks like this. It's the probability of each frequency converted to a signal strength. If that frequency is more likely, it's a taller peak. That's a direct scaling. And this is an inhomogeneous superposition of all the different orientations. This peak pattern pouch. This concept is important in solid state NMR because with or without magic angle spinning can come up. So go back to this cartoon I gave you before about magic angle spinning. You got these peak patterns for simple organic solids that cover the whole spectrum, you know, from 0 or even slightly less than 0 on up to 200 for a diamagnetic organic solid. And they're not resolved, and there's really limited amount that you can do with them. It's not nothing. It's not nothing. People learn a lot of things about polymers, but it's pretty good. And then in the 50s, independently, 2 different British physicists thought about a clever idea, which is to rotate the sample mechanically. That's time averaging the instantaneous frequency. And the question is there a geometric trick? Is there a best angle that if we rotate the sample around that angle, it'll look as much as possible like the solution NMR, which involves nano to picosecond random moves in space that are almost equally weighted. Okay? By here, we have a different approach. It's not picosecond or nanosecond. It is millisecond to microsecond. It is not random. It's a harmonic Hamiltonian, which is a special and interesting area of quantum mechanics. So, but could it serve the same purpose? Could it average in a way that emphasizes the isotropic value? And it was discovered that this does work. And the case that I'm going to be talking about is strictly for a second rank tensor, but otherwise arbitrary. In NMR, we do encounter higher rank tensors, things that depend in a more complex way with the space. We're not talking about those here. Examples of that would be cross terms between 2 interactions or the electric quadrupole interaction. There are other examples. So we're not talking about that. We're talking about just CSA, just dipole things everyday terms in your Hamiltonian. There exists an angle such that if you rotate your sample, you get a liquid-like sharp line at the isotropic shift. And if you rotate more slowly, this funny thing happens that we call spinning sidebands. So you get sampling of the powder pattern. You learn something about the powder pattern and you get to probe it at places flanking the isotropic shift spaced by integer multiples of the spinning frequency, like a harmonic series. So how does this work? And we're going to treat this with the rotation angles that we just developed.
Oh, and you got to know historically whether they did the theory first and then said, we need the magic angle, or are they mucking around experimentally and then got the theory later?
Lowe knew that this would work. An interesting thing about the early experiments that Jay Schaefer, who has to restore some kind of, but did a lot of early magic angle spinning spectra and spent his career at Monsanto and at Washington and St. Louis. He mentioned to me, like he and other people had just had so much excitement about using magic angle spinning to advance solid NMR. But for the longest time, they didn't know how to make a sample holder that would be hollow that they could spin. It was enough of a mechanical engineering achievement to just study the cylinder itself. So they were studying rotors. And that went on for a while, like polymer chemistry. So why gypsum? Why a mineral? Why things like this, you know? And for many years, until I would say about late 80s, something like that. Mainly they would have been home built. And there were small outfits that made these for a very small number of clients. And one of them was in South Carolina, and I went to work with them because we were trying to get our speed up from 4 to 8 or 11. And we were so excited about this. For the proton NMR and the paramagnetic system, we were so excited about going up to 11 filter. And I think that now what we're doing is arguably the highest frequency mechanical spinner for any application of any form. Folks go routinely to 60, exceptionally to 100 or 200. I don't think there's an example of any dental drill bit or anything else out there that does that, the aeronautics or no other call for it. Yes.
The faster rotor is better as of like more like sharp signals.
When do we want the faster rotor? Yeah, there's a trade-off, and maybe we'll talk more about that later. But one thing to consider is the speed of sound. We do not cross the sound barrier. We don't have a Concorde yet. I don't think we will have one. So we are limited in volume because of the surface bonus. And that's a double-edged sword. Like, we're a little confused about whether we want a big volume or a small volume, I would say, a little bit cognitive dissonance there. But you end up with very small samples. The other thing is that the rapid rotation, averaging on a faster time scale, can sharpen some sources of line width. Some kinds of dynamics, many kinds of networks of coupled spins, where it's not just an IX spin system, where it's more complicated than that. And spinning faster helps almost as the square. It helps a lot, and higher field helps a lot. So the more you can truncate it with the high field, the more you can spin it, you really get a lot of benefit. But if it's all inhomogeneous broadening, which I used to think was true, and that's too extreme a view, I wasn't right, but if it's all inhomogeneous broadening, that you have, partly because of the way we treat our samples, so you have a little bit that's a little bit dried out, you have a little bit of this, a little bit of that in your rotor, then spinning might not help. The high field might not help. So it depends, where is your line width coming from? Does that make sense? Okay, I was going to talk about the problem that's in front of us, which is if we start in a molecular frame, and I'm drawing a little crystal that I had to use some tweezers and place into my rotor, okay? This is my cup, my rotor, and then I've got this crystal inside it. The crystal has its set of coordinates. The rotor has its set of coordinates. That's a frame transformation. I don't care about the rotor frame, it's an intermediary frame. I have actually the principal axis system that I can get from a paper. So arguably, it's not the same necessarily as the crystal fixed frame. So arguably, I need to even go one more step back and say, here's my functional loop. Yeah, and it has a Z and an X. And I need to take 3 Euler angles, or maybe only 2, and move that into a crystal fixed frame. And now I have a crystal fixed frame where this is Z instead of, like, actually it would be into the board, but instead of the molecular degrees of freedom, I now am in a frame defined by the crystal. Now I place the crystal in the rotor. That's a choice, and I describe that choice with 3 angles. Now I place the rotor in that field and rotate it. I can cover both of those operations with one set of rotor. So the crystal to the rotor frame is a time-dependent motion that I at least think of as a compound motion. It's moving Z and rotating around the rotor. So I hope you're not too disappointed if I say that I'm going to combine these two. I don't want to do 3 frame transformations. I just want to do 2. All right with you? People are mad. I'll prepare the other one for tomorrow. Then you'll be mad again. So we're going to pretend that the crystal fixed frame and the PAS is a thing. I mean, of course, it can't generally be so. And when does that matter? When we have 2 different interactions that we're going to combine. And they both sit in the crystal fixed frame and they're not. both the same as the crystal. That's when it matters. Also, if you had some molecular motion like that. Anyway, we're gonna pretend that we can line that carbonyl up perfectly with the crystal, and we'll just have one set of angles. They are time dependent. Alpha, beta, gamma does not depend on time in this problem. And quite often it's a random number generator, a special random number generator, a smart random number generator. You just play the crystal, any crystal, that kind of thing, okay? And at the end of the lecture, I think we'll look at spectral crystals, like pathological crystals that are placed in the body, if we have time. And then this, what is this? This says, take the z-axis of the rotor and view it in a lab frame. So that's a rotation around y, moving z from the rotor to b naught through an angle. And I'm already going to start calling it magic, even though we don't know what's magic about it. Okay. Then after that, what do I need to do? I need to rotate it around z of the rotor frame. We're going to be rotating it around z of the rotor frame. And actually, in terms of the operation, that's done first. Once we get it into z, as the laboratory frame is uniaxial, we don't actually need to bother with glass rotation. Once you line your crystal correctly with respect to z, the lab doesn't know the difference between x and y. So we can put random numbers in here for gamma, or we can put something there for gamma, but we actually don't need to. It's an unnecessary thing. So let's just make a few more remarks about this. Alpha and gamma describe the PAS relative to the rotor. It's used to build up the Pao pattern. Omega RT, progress of the rotor, and theta M, the magic angle, which you empirically set as you do your experiment. These describe the rotation of the rotor. Now, gamma is like, where did my rotor start? You know, omega RT is my progress, gamma is where did it start. Sometimes, I don't know that we're going to make you do this, but sometimes it's good for you to confirm when does gamma matter and when doesn't it really. I just said, don't worry about it. But maybe we should talk about that there are cases where it can matter and cases where usually it's handled implicitly by the power pattern analogy. So alpha here, I'm going to get rid of saying, so I want to simplify this. So alpha here is needed if and only if the interaction is not uniaxial. That is, if it's rhombic or asymmetric. So that's a typical CSA. You really should keep that alpha in there, but I'm not going to today. If it's uniaxial, the conversion from PAS to RFF, you could just start directly with the rotation around Y to line up their Z axes. If it's uniaxial, I'm free to pick any Y that's perpendicular to Z that I want, because that's a Y or equivalent. So I pick Y as the node line that we defined yesterday. Node line, the mutual perpendicular of old Z and new Z. I can pick any Y I want in the PAS, I pick the node line. So then I don't need a pre-rotation. I just go directly into beta. Since the frequency measurement, I said this already, but I'll just say it is truncated, and the magnetic field is uniaxial, gamma prime is not used. Once I get the RFF correctly into the lab, it doesn't matter if I have X or Y.
And maybe you told them this yesterday for the before you let them do it. But with the rotor at the magic angle, where's the coil?
Coil always snug up around. We can have a lecture where we talk a little bit more about experimental things, but the coil is always snug around the rotor if possible. If possible. Now, if the coil can create problems if it's too close, it can rub, it can arc, it can have susceptibility issues that ruin your shimming. Having it too close can interact with sample. There is such a thing as too close, but mostly if we could get it as close as possible, why? Why do we want the coil close to the? Yeah, and what else? You want the signal and you're close. There's such a thing as a filling factor. If you have a great big old coil and your sample occupies a small fractional volume, that's a fraction. We don't like to do that, right? But that does mean that the coil itself is at the magic angle, and that there are things that we could discuss about the projection of the pulses, X and Y. But maybe we can come to that when it suits the lecture, yeah.
Sorry, I shouldn't catch this. Did we say that the gamma is where the rotor's z-axis start, or like?
Gamma or gamma prime?
Well,
In this one?
you're talking about.
This is just, I'm placing my crystal
Yeah.
in the rotor, and beta describes the tilt, and gamma describes what I did with this in terms of the crystal, which doesn't matter.
Oh, I was talking about the rotation of the rotor.
That's gamma prime, this one?
Okay, yeah, you said that
Mhm.
gamma describes when does it start, when does the rotor start?
Yeah, you can think about it that way, like E. This is the progress of the rotor, this is the magic angle, and this is like, at the time you pulse, for that particular crystal rotor. And for many pulse sequences, this turns out not to matter when we do the power average. But we're not guaranteed that it does matter, so we can come back. All right, so we have a problem of two rotations. I like these cartoons. Two rotations, where in the PAS, we might have only this if it's uniaxial, like the dipole coupling, or we might have this and this if it's a general CSA. In the lab frame, and as always, we're just calculating the instantaneous frequency, so we just need m equals 0. In the rotor frequency, in the rotor fixed frame, I'm going to include them all. I don't have any a priori reason to discard it anymore. So we've gone from a pass-through single calculation to all of that. So how would you guys like to do the uniaxial case first? You like that? Okay. So we're going to get rid of these three. We're going to leave these three and these three. I call them three. This is two different components, and this is two different components. But the terms look so similar, and you'll see that I get to rewrite them as being sine and cosine. So I gang them together. Okay. So we're doing this. Three groups of two-step pathways. So two rotations, so you'll see two of those reduced figure multiplied onto each other. Two rotations in a row. In PAS and lab, we only have 0. So what I'm going to call M and M double prime are 0. In the RFF, I believe M prime has to be allowed to take any value, as long as it lands where it's supposed to in the end of the problem. I ignore this. I don't know why I have so many rows. So I'm going to have two rotations in a row. I drop alpha, uniaxial. I drop gamma prime. I asserted that I can do that. So I've got 4 angles I need to tend to, and one of them is a pi angle. It's a function of mu. Go back to the general expression and see where we stand. Okay, choose an interaction. Maybe dipolar. Choose L, always 2. Sum over M. So we have to go and sum up in the lab frame. So T stays in the lab frame. We don't have to do anything for it. R, I don't know how to write it in the lab frame until I do my ignorant stuff. So I start with R, and I have L, M double prime, and I just said I'm totally going to have M double prime equals 0. So then I have these sums, but everywhere I see M, I get to put 0. Everywhere I see M double prime, I get to see 0. And keep in mind, of course, when we do these sums over domain variables like this M prime is going to be the same as this M prime. So I have 5 different sums, but I kind of think of them as 3 sums because the plus and minus 1 are so similar. Plus and minus 2 are so similar. Okay, so gamma T20 for CSA in the lab, if you choose that one. R20 for CSA in the PAS. And then the Wigner rotation for 0 beta to, I left gamma not alpha. It's an inconsistency with my last slide, sorry about that. And then this is, oh, no, it's consistent. This is from the crystal fixed frame to the rotor frame. I left out alpha, and I have beta and gamma, okay? And then here is from the rotor fixed frame to the lab. I left in alpha, beta, and I dropped out gamma. So this collects down, subbing in for everything we know, becomes this expression, not that bad. And it's the sum over all the n values. So we'll have 5 terms. It had these assumptions: uniaxial, truncated, one interaction, L equals 2 only, and lab and PAS are fully truncated, just the one self. So what we have, we'll have 3 terms. And in general, they'll look like this. E to the minus IM alpha, that's the phase factor for placing the crystal in the field. But I happen to know that M is 0 and alpha doesn't matter, so that's 1. Reduced Wigner, explicit function of beta, which is the crystal powder averaging index angle. And I only need that for 0, 0, 2, 0, 0. You remember what that is? The reduced Wigner for L equals 2, and both values of M are 0. Do you know what that is? Second Legendre polynomial. You will be friends with the second Legendre polynomial. Okay? That one is the only one I can do, like, you just wait, you have 2 of them. The rest of it I might have to cheat a little bit. Okay, and then this is e to the I m prime gamma. Gamma is for placing the crystal in a rotor. And actually, I think I may have confused you, when you asked me about gamma and describing where it starts. I might have pointed to the wrong gamma. This is the gamma that comes with the crystal averaging, that is the start point in the rotor. That gamma, the one that goes with beta to build up your power pattern. Earlier, when you asked me that question, I may have pointing at the wrong gamma for some reason. Okay, so you're placing your crystal in the rotor, and you have this P2 cos theta business, then you have e to the minus I m prime gamma, and I cannot ignore that this time because m prime is allowed to take values from -2 to +2. Now, on the other side, I have e to the minus I m alpha prime. That's m, not m prime, and I said m was 0, so that's just 1. And d of beta, that's the magic angle. And e to the minus I m prime of gamma. So the inner term, which should, I just have a typo. I don't think I can fix it properly, but I can fix it a little bit. That obviously M prime, the counter for the rotor fixed frame, has to come up twice here. And on the last slide, it was correct. But on this slide, not. It should be right here. I'll fix it for real later. Okay, that's a horrible end run. But it's a reminder for me. Okay, so we're starting in the lab frame where a PAS frame where M is 0. We're ending in the lab frame where M double prime is 0.
Hello. Excuse me.
The last operation
Hello.
moving to the rotor frame and the first operation getting out of the rotor frame, our counter is M prime. Those are the
Quick
ones.
question.
So we have two terms that look like e to the minus I M prime. And one of them
Hello. We
is
can't see the
the
slide anymore.
last angle
slide.
for placing the crystal in the rotor frame. And the next one is omega RT, the one for the progress. Somebody has a question?
This- yeah, the slide. So I mean, I can't see it anymore. The slides for those of us on Zoom.
Okay, thank you. That volume is for that, and I don't actually have authorization. Yeah, why did that? Thank you for pointing that out. We can barely hear you, but we're gonna fix it.
All right. Thank you.
Okay, is that better?
Not yet. Let me check.
It's good. Thank you.
Thank you very much for pointing that out. I'm sorry, we just could only barely hear you, but we fixed it. Okay. So this is our rotation. Two rotations, actually, back to back, 3 frames, starting us in the PAS using a polar angle beta and an azimuthal angle gamma to place our crystal. Another azimuthal angle that adds directly onto gamma to represent the progress of the rotor, and one more polar angle to bring Z of the rotor to the lab frame. And once we're in the lab frame, we don't need to do another azimuthal angle. I want to take a minute to pause here, especially because there was one thing about those 2 gammas that was corrected a minute ago. Just make sure everybody's okay, that you have any other questions. So the expression is massively simplified, and I'm ready to start to fill this in and get a recognizable equation for the frequency. So just how did we get here kind of questions? What did the symbols mean? How did we get here? Anybody have any questions? Yes, please.
So for the leftmost D, your subscripts is M prime and then M. Why is it not the other way?
M prime and then 0.
Yeah, why is
Well,
that?
it's going to be 0 M prime. Is that what you're saying?
Because you're going from.
I actually think you're right. I think you're right. I think that should be fixed. Now, I think it's symmetric, so it won't change our answer, but I think you're right. Yeah, thank you for getting that. What's your name again?
Even?
Ethan.
Yeah.
Thank you, Ethan. I'm not gonna fix my slide because last time I did it, I messed up the whole Zoom, so. Okay, so
He's thinking of the purpose of this.
that's a way to keep you awake. If it was like a freshman chemistry class, you get clumps. Fine, it's like candies. Okay, so this is what we did. We start from M equals 0, we move into the rotor fixed frame where M is anything, and then we project onto the lab frame M is 0. And we have now an expression for that. However, I didn't write it out, so let me do that for you. So, top line is what we just talked about, and it still means Ethan's correct. Okay. And the middle line, I started to fill things in. So I combine terms, phase factors, azimuthal terms in the middle. I combined them. That's about all I did, and started to write them out. So the 0, 0 term It's the reduced Wigner for beta and the reduced Wigner for the magic angle. And then a phase factor, which is gamma, which again is like the initial rotor position, and omega RT, which is like its progress. Now we have another term where we take that in the rotor frame, we have n sub L equals 1. And I'm writing it right next to the n sub L equals -1. And it looks just the same, except for that index, and also the fact that the phase factor now matters. The phase factor is not 1 anymore, it matters. You have to keep track of your gamma plus omega RT. And then the same thing for m sub L equals 2 or -2. And I go to this table and I start filling in the reduced Wigner elements. So that's for the m prime equals 0 term. Is everybody with me? Yeah, I went to the 0, 0, and I found this thing I, and that's my favorite Wigner element. And there it is twice. Because it's 0 and all 3 right. Now, what if I start in 0, I jump to 1 or -1, and then I jump back to 0? What does that term look like? Well, I need something like a 0, 1. Or a 0, 1 this way, or so they're all G or -G. And so you pull this out and you keep track of your plus and -1s, and you get something like this. Now, at that point, I had 2 such terms. I had the one where in the rotor frame m is +1, and the one in the rotor frame being -1. And so there are 2 different phase factors, but it turns out that the product of the 2 Wigner reduced Wigner elements is the same, other than a sign. So I had this nice little compact expression, which felicitously can be rewritten as a cosine. Finally, let's put the rotor frame to m prime to being 2 or -2. So it always starts or ends in 0, starts or ends 2 or -2. That's always C. So those will really combine nicely. You don't even have to keep track of minus signs. This expression, root 3 over 8 sine squared beta, and you end up with this for the projection factor and this for the phase factor. And that also can be rewritten as cosine. That mess, if you recognize it, this is not intended as being a vector. This is this plus this plus this. That's the frequency. As a function of time during MAS for a uniaxial interaction. That's what it does. I think I have a visualization of it next, but maybe just look at it. It has a constant piece. It has a sinusoidally varying piece, cosine, and then it has something that moves according to double the actual rotor frequency. You move the rotor once per day. This Hamiltonian moves itself twice per day. This you see in NMR problems involving second rank tensors. Why? Because when we rotate the tensor, we are obliged to do it twice. It's a bilinear operation. It's the outer product of 2 vectors. It needs to be rotated twice. So you end up with double frequencies in everything that you do, and not just MAS. So again, some of these 3 terms. So this is a little bit about the angle. Like, we're not allowed to pick angle that. Oh, and you might have seen that, maybe not, because these experiments aren't that popular anymore. Some of you aren't doing magic angle treatment. If you had something that wasn't a second prime tensor, there are other angles to rotate around. I don't know if you've seen this before. You have a quadrupole. There's this total high wire experiment that was developed by Phil, Randy, and others when they were in the Pines group, where you take a rotor and spin it up as fast as you can. It'd be very tiny. That sits inside another container rotor. And so the air has to be directed within the outer rotor to spin up the inner. Kind of cool engineering problem right there. And so you have an air jet that just doesn't, it's not like with our rotors, you have flukes, you have a cylinder and on the top you have flukes and you just, little stream of air, right? Here, you gotta get some kind of airflow so that you spin a rotor inside the rotor. And they are sitting at two different angles, which is
Are the two rotors attached to each other? Or?
free floating, suspended. Okay, you may be able to intuit why we don't do this every day. There's also start and stop, which I thought was a very cool experiment, but it's very annoying to have a desk next to that. You can hear the spinning of a rotor. It's enough, audio frequency. It's not going to go up that high. If it goes up to 4,000, it goes up to, the high notes on the keyboard. And all the way down. And then all the way up, Okay, but then there were also variable angle spin, so you can move the angle. We're free to ask as experimentalists, what angle would we like? And people have done some pretty impressive mechanical engineering to make all of the above possible. So what angle do we want and why? I want to talk about the properties of these three terms, and I'm going to start at the bottom. Oscillation. It has an amplitude and a cosine variation, linear argument in time. How's that going to behave? What kind of properties does that function have?
I guess if you're oscillating very quickly, then it will average out to zero.
Should average to zero. And even if it's not fast, there's a really clever thing you can do is only sample at the end of the rotor period. And there again, it will act as if it's zero. And that's what people used to do. Rotor synchronous sampling. So that term is really good. It's like a good term. How about the one on top of it?
See?
Yes. So we like it because it's time dependent. It does depend on the crystallizing angle and everything, but every single crystallite will average to zero. Now, what do you think about the top term? What are its properties? Does it have any time dependence? No. Is it zero?
Use the right angle.
Is it crystallite dependent? We're gonna get a little powder pattern. We're gonna get a little powder pattern. And remember, every crystallite you have to add all three terms. This isn't sometimes maybe, this is like on every crystal. You add up the various crystallites, you've got the same dumb powder pattern you started with. I mean, it's a little smaller. Or wait a minute, if we pick, as you said, if we pick the magic angle to be a very smart choice, maybe it's essentially gone with an experimental error. So the problem with it, it's crystalline dependent and time independent, needs to be zeroed. And you zero it when you choose the cube diagonal. When you choose the answer to this problem, 3 cos squared theta magic angle minus 1 is equal to 0. Okay, that's an angle that represents the cube diagonal. And it comes up in other physics problems, but for chemists and spectroscopy, this is kind of an unusual example. If you pick that, then that whole expression becomes this. You know what the value of this is, so that becomes a fixed number. That term's gone. Whole thing averages to 0 along the lines of what you indicated. And so it's a function of time, rotor frequency, and 2 angles that describe which crystallite you're talking about. So if you correctly set the magic angle, you lose the first term for all crystallites. I have a problem in the problem set that asks you to think about how accurately you think you have to set that angle. Now, you could just take this on as a math problem and not really give it much thought. But when you're done with it, I want you to stop and think you have to build a mechanical object that sets things reproducibly to that accuracy. And tell me if you think that's like a middle school project or, So the misset angle, would have, things we don't want, power patterns on every single, term, on every single, term and, every single line. So the anisotropy won't contribute to the average peak position. We will get the isotropic shift if the angle is set properly. We already commented on the presence of a double frequency, that's a property of a second rank tensor. And I want to comment that there are special crystal orientations. They don't matter very often, but it's just sort of interesting to think about. Special crystal orientation on the rubber beta equals 0. The PAS is already along the magic angle. It won't have any time dependence. It's always isotropic anyway, all the time. It didn't need the rotation. These can be pathological in terms of their rotation properties or other things. Now, it's a handy way to summarize the answer to the problem we just did. And I want to remind you that we were in a rotating frame that is not the Larmor frequency, it's the isotropic, different to what we usually do for solution NMR. So omega of t, explicit function of t, is omega iso, and then an amplitude times this cosine. This is the argument. Another amplitude cosine of double the same arm. And these are our geometric vectors. This is strictly true for the dipole interaction. Strictly true for the dipole interaction, whereas it was the approximately true for most CSAs. So let's deal with the approximately, but first I'll just give you these graphical illustrations that come from a nice concepts of magnetic resonance article. I don't know if you guys make use of these. There are some that are very good on the spherical harmonics and the bigger rotations. There are some that are very good on basis of solid state NMR. I give you a citation to one of them. Len Mueller, for example, does a lot of these that are really good. Anyway, you have different crystallites and their frequency, or just the angle or the frequency, either one, is, I'm sorry, I said angle, but I meant the bigger rotation element. Unique to each crystallite in terms of how it was placed in the rotor. But in general, you get these kind of patterns where here's a full rotor cycle, and a second rotor cycle, one full rotor cycle, a second rotor cycle, and you can have the dominant presentation of the harmonic, or you can have one that looks like it's mainly sinusoidal, but it's just a little bit off of a sine function. So each one has that kind of frequency trajectory in time, where it's very frequencies coming and going, and it's not a cosine, it's something a little more complicated. So let's sum up and then decide what to do next to the group. So if the angle is set correctly, the rotation is fast enough, dipole anisotropy averages to 0. CSA averages for the isotropic shift, and so overall you just have a spectrum of isotropic shifts if you sample properly or spin fast enough. So otherwise, you will see that you're taking data points that are not just the isotropic shift, that they have some pollution from that funny pattern we just saw for the frequency of function time. We're going to get into that. What is that? You have this sinusoidal variation, complex sinusoidal variation in frequency as a function of time. And if I oversample, spun slowly, how does that work? There's a mathematics that goes with that. At the end of every rotor cycle, though, it'll be well behaved. So I would strongly urge any of you who are going to do magic angle spinning to rederive and follow everything I did and see if there are any more questions for typos. Or strongly urge you. That's probably the best thing for the beginning. Solid state spectroscopist. I also just want to share with you, without driving, what happens if you put data active. And any of you who want to go over this, we can do it. We're a little cramped for time, and it's really a question of changing on where the bigger. So I'm not sure if it's a good lecture, but I'm happy that we work it through in a problem session or whatnot. Yes, please, Chris.
So if you don't have a uniaxial system, will your it's like the same choice of the magic angle will zero out. So
It is the same choice of the magic angle, because we chose that based on that time independent, but crystal-like dependent term. That's the troublemaker. So if you put eta back in, here's what you get. You lose the time independent term if you pick the right angle. You have the same two cosine. What it brings to you, it turns out, is some sine varying terms. So the trajectories of frequency with respect to time are just that little bit more complicated, but they still look like, trigonometric functions, sines and cosines. And here are all those amplitudes. So you get two more terms there on the time dependence, but no new frequencies, and it's not a different angle because there's no change in that time dependent piece. So where I want to go next, and I'm going to suggest that maybe we turn to problems if folks want to, and we do this if I have Art's permission at the top of tomorrow morning. We have an expression for omega of time. We actually want a spectrum. And I have a plan for that, so we can go over that, and I don't think it'll take the whole class. Okay, so how do you get from omega of time? Normally, you just had omega. You just had omega, and you said, hey, let's enjoy a Lorentzian, and we slapped that on it, and then we were done. But now, omega is like doing this, we're trying to take a spectrum somewhere. What do you do with that? Other questions before we take a little break? Okay.
Maybe I would just say what's coming after this is we're going to be doing for solution realization, a transformation from the PAS to a molecular frame, the diffusion tensor frame, and then from the diffusion tensor frame to the lab frame. And that first rotation, just like now, will be independent of time. The diffusion tensor frame is like the crystal frame. And then from the diffusion frame to the lab frame will be time dependent because the molecule is rotating due to rotational diffusion. But it turns out for relaxation, we have to keep all the terms. We don't get to simplify that. It's just the n equals 0, 0 term. We have to keep them all. But the math is the same. So if you do this, you're in great shape for relaxation here.
Shall we take just a few minutes? And those of you who have turned in homework, that's fantastic. Those of you who might not have, maybe hints, we can do that. We're not going to stand on ceremony. We want to get you all to actually do those problems, and then we'll have other problems to actually do next week. It's your best path to absorbing this, is to work problems.
Could I ask this silly question?
Of course.
Why are you guys just not spitting the whole sample? It's like if you just packed it, if you were that looked like a ball, and then just like, is that mechanically hard?
Why aren't we using a spherical and random operation?
Yeah.
Okay, so for a long time there was a resistance to that idea, based, I think, on the idea that it would take too long to sample in a representative enough. Sorry about that. in a representative enough way to average to the isotopic. So here, we are guaranteed that after every rotor cycle, we know, right? And I think most people assume that you need a very long random walk. Anyway, a few years ago, somebody who loves engineering, especially the intersection of mechanical engineering and electrical engineering and NMR, named Xander Barnes, who studied at Bob Griffin's lab and then Lynette Sigelski, and then he was an assistant professor at Washington St. Louis, and now he's at the ACAB. He started making these spherical rotors that pursue exactly the idea that you're asking about. As you can write your paper on anything you want, you might just Google and see how's he doing with those spherical rotors. This guy makes a lot of different things. Last time I saw him, we invited him to speak at a workshop on dynamic nuclear fluidization, and he's walking around with this jewelry he had made out of magnets that they're making in his lab. They don't want to buy magnets, so they're making magnets. They're small, they're very small. And a very presentable piece of jewelry. So they're making all sorts of things in that lab. And that's one of the spherical rotors. So how did he address the question I just posed? How do you sample representatively under useful time? Also, when you have a cylindrical rotor, the idea was you could float with a cushion of air, and then so it doesn't rub from on the bottom, and then you could have a directed set of air across the fluid.
And they have feels like dipole.
What's the deal with the spheres? Where's the cushion? But you could find out a little more about that.
Slightly more complex,
But the
because we didn't talk about the comparison between the anisotropy, the magnitude of the anisotropy and spinning frequency. So, like if you have a 50 kilohertz dipole, there are 10 kilohertz MAS.
And look a rotation of an ellipse. So now our NMR
Like it gives you
cylinder.
technically gives a side band. Yeah. Mostly for protons, which is 10 times decoupling. And then for homonuclear coupling, it's a whole different story.
You hardly need to shim.
wait, do you not get those like same terms if you calculate like the dipole coupling with the extra rotation?
Yeah, but the dipole coupling, homonuclear dipole coupling, the spin Hamiltonian is a little bit different, and you have generate terms where you have at least 3 like spins. This question is right, what happens to the dipole coupling under that? I've tried to explain that. At least with the network of homonuclear couplings, it's not as straightforward as getting into side bands.
Yeah, if you had only 2 spins and they were isolated, it would spin out perfectly. No problem. Like it spins out very, very nicely, even for strong couplings. And you can see that when you simulate, but it's hard to engineer a sample like that for the reason that Anish was saying. So do you need help and
No, I think
hook up or just give me a shout or I can go get in.
And when you think about the question of how difficult is it to build something, imagine if we go with the tuning. I kind of running yoga was you build it out of Legos.
I'm more with the 3D printer. I already
Say build it out of Legos, it's simple, not complicated. Some years ago, high school did build an atomic force microscope out of this Lego set, and it worked.
Okay, so I don't have too much of a structured session today, other than perhaps giving an introduction to one of the problems and some of the problem that assigned for next week. So next week assignment is problem 8 and problem 14. I'll do that. Yeah. I will share my screen. I'm just addressing it right now. 8 and 14 from the same problem set. And 14 is the problem that talks about dynamical averaging of a CSA tensor. So it's kind of analogous to what we will go on to discuss in solution NMR, which is chemical exchange. But this is like we calculated the frequency, therefore the powder pattern for a CSA tensor with a set of principal components. But then you imagine that the functional group is undergoing some sort of motion with a certain symmetry, like a methyl group rotating around it, or the 3 protons rotating around the symmetry axis of the methyl group, or the flip of a phenylalanine hydroxyl or a tyrosine ring, for example. So, if my computer is cooperating. Before that, do we generally have questions from attempting the first problem set, like places where, like, give me a hint, give me some,
Can you look at problem 3?
Oh, 3, okay. Uh, let's see what it is. Let me just share my screen before I get started. So then we have slides, the notes, and one note open at the same time. And look at whatever you want to on the screen. Okay. Good now. Let screen. And that. Now if I change tab, will it tell me something? Given these. Yes, this is an important problem. Okay, so we have a request for 3. You have anything to say about?
No, I was just saying, I didn't really, I guess I just don't know what the crystal frame was compared to the.
So crystal fixed frame in this case is the XYZ frame in which you are given the coordinates of the atoms in glycine.
Okay.
Does that make sense? Like there is an arbitrary origin. There is an origin somewhere. Relative to that origin is an X, Y, and Z, and in those X, Y, and Z axes are coordinates of the atoms of glycine. And the question is asking you, like, the angles for the rotation from crystal fixed frame, the principal axis system, of the carbon-carbon dipolar interaction, and the carbonyl CSA. So
you need the actual crystal of SC? Like, do you need to know the actual?
No, it's like saying, assuming that you have
I see.
X, Y, and Z coordinates for all the atoms of glycine, and those X, Y, Z coordinates define the crystal fixed frame.
Okay.
Given that information, how do you obtain the Euler angles for the rotation either from the carbon-carbon dipole coupling to the crystal fixed frame or from the carbonyl CSA to the crystal fixed frame? So the CC dipole is uniaxial and the carbonyl CSA is not. So accordingly, you have either one angle, two angles. Okay. Oh yeah. Then generally you can find definitions for the direction cosines there that you'll have to obtain from like calculating the vector or the individual vectors for the three tensor components in the prescriptive strip. Does that help?
Yes.
Yeah. Okay. Okay, so we had 7 and 9 as our assignment. I'm just going to do part of problem 7 just so we get some review on what we've been doing, what we were discussing at the start of class, which is how to break down a Cartesian tensor into its spherical tensor components, and then how do you go from those spherical tensor components to a frequency by performing the correct rotations. Okay. So this problem is asking you to do both Cartesian and spherical harmonic to derive an arbitrary tensor from principal axis to lab fixed to an arbitrary set of Euler angles. Okay. So is this the correct? I mean, I hope we've seen this enough that we agree that this is the diagonal, traceless diagonal for the shielding tensor in its principal axis system, right? Here again, just to sort of orient all of us, remember that you may see different notations in the literature, and you have to be careful about like how these components are defined. So as we had done this last time, delta here refers to the ZZ component minus the isotropic component. And for simplicity, I'm going to assume the isotropic component is 0. So then I can just rewrite that as this. And eta here is the yy minus the xx divided by the anisotropy. Okay, this is one set of notations you will solve. If you look at some older literature, you might find terms like pan and skew, capital delta and kappa or something like that. And those are again like numerical multiplications of these two components. So we're going to use this notation. And we're going to see how well we can rotate from the principal axis system to the lab frame, the principal axis frame to the lab frame. Last time I showed you how to do this using an actual rotation of the B naught and the angular momentum operator. So we applied the rotation matrices and calculated out the frequency in Cartesian terms. And today I'm going to sort of talk about how we can arrive at this using spherical tensor notation. And of course, the important thing is, well, let me first ask this question. This is a tensor of rank 2, as I hope we all agree. And a tensor of rank 2 will have, as in principle, 5 components, right? Which of these are non-zero for this tensor? Zero, 2 plus minus 1, and 2 plus minus 2. Which of these are non-zero for the CSI tensor in this principal axis frame? 2, 0, and 2 and plus minus 2. If eta equals 0, then only the 2, 0. Let's verify that with the formula. You want a general formula or formalism for converting the Cartesian tensor into the spherical harmonic tensor. This is how you do it. Right? So this is assuming that you have a 3 by 3 matrix that is representing the tensor of interest in a given axis system. Any axis system. In a given axis system, I get these 9 terms. I get 9 spherical tensor components out of 9 terms in the 3 by 3 matrix. And you can see that M00 adds up to what? Is the trace of the matrix, and this is true of all n-rank tensors. The M00 component is always the trace, and you're using a traceless diagonal form, so it is 0. Similarly, if you see 1, 0, 1, 1, and 1 minus 1, it only involves off diagonal terms, right? That makes sense? Only involves off diagonal terms 1, 3, 2, 3, and 1, 2. And we've kicked out the antisymmetric part of the tensor as an approximation, in the sense that we said it does not contribute to the frequency. It contributes, as Adnan would explain, to relaxation, but we've taken the shielding tensor, broken it into a symmetric and an anti-symmetric component, and said the anti-symmetric component is not relevant. So then you arrive at these 5 numbers: 2, minus 2, minus 1, 0, 1, and 2. And so M2 minus 2 will be given by the formula is half M11 minus M22. Right, so I'm going to ignore the other part because that is obviously which turns out to be is there an over 2 or
These are what happened here. So
yeah, but you should get simply yeah, there's another after. That right? Does this make sense? And by symmetry, you will find that the M22 component is the same. The M21 and minus 1 components are 0 again, because they only involve off diagonal terms. 1, 3, 3, 1, 2, 3, 3, 2, 1, 3, 3, 1, and 2, 3, 3, 2. So 1 minus 1, 2 minus 1 and 2, 1 are again 0. And then finally you get M20, which is just the anisotropy. The square root 3 over 2 Does this make sense? So what I've done is I've taken the traceless symmetric CSA tensor and broken it down into components. The components being what we have described as like these eigen operators of RC, the basis, the spherical harmonic basis. So I've taken a tensor, a 2-rank tensor, and I've decomposed it into a spherical harmonic basis set. For me, this was sort of the analogous to how you would take an arbitrary wave function and break it down into eigenvectors of the Hamiltonian, eigenvectors of a special operator, taking an orthogonal complete basis set, which is orthonormal in the sense that each basis component is normalized and any 2 basis components are orthogonal to each other. So you take a complete spherical harmonic basis set and you take the Cartesian tensor and break it into and you ask which components exactly have non-zero terms in this representation. So we find that 2, 0, 2, 2, and 2 minus 2 are the only 3 components which have non-zero contribution to the traceless diagonal CSA tensor. And that contribution as kind of like the coefficient. It's kind of like because I like analogies of quantum mechanics. I'm thinking about linear algebra. C1, C2 are like how much amplitude you have for those basis functions in your wave function stack. Similarly, this is representing how much of that spherical tensor component is present in your physical diagnostic data. And of course, if asymmetry is 0, then 2 and 2 minus 2 disappear. You only have the 2, 0. So if I were to take an diagram for thinking about rotations, I have in the PAS frame, I have a small m equals 0 component, and I have small m equals plus minus 2 component. So this is square root 3 over 2 delta. This is minus 8 delta over 2. So m equals plus minus 1, I don't have anything. Okay. And what I am trying to do is I am trying to rotate this into the lab frame. Now in the lab frame, which is the only component that matters? Okay. Only this component I need to know. Right? In principle, this will rotate and give me all 3 terms. But the last 2 are irrelevant. That's again because of truncation. So this theme of truncation keeps coming back to us in NMR generally and in solid state NMR in particular, where 2, 0 again we picked up as we discussed last time because P naught of course is only along Z. We also say that the induced field is important only along Z because the induced field along X and Y is going to be so small relative to B naught that its effect will be trivial. So I reduce the angular momentum operator to IZ. And when you take BZ and IZ and cross set, you get just the Z zeta, which is the 2, 0 component. So these rotations are irrelevant, and these are the only 2 rotations that matter. I have to rotate through an arbitrary angle configuration, alpha beta gamma. So I have a general CSA tensor given by delta and eta, and I've broken it down into the spherical tensor components, and I must rotate it to this angle. Any questions so far? Yes.
It's like we never do the 90-degree pulses in like solid state, right?
Not sure I understood.
Like when we were learning solution, like we would do a 100-2 pulse to like kind of amplify the signal.
We're not talking about RF. I mean, you can still do a 90-degree pulse in the solid state, because the point of a 90-degree pulse is to create a phase coherence in the transverse plane that you can then detect. Right? So there is no reason to believe that you. I mean, is there something I'm missing about your question?
No, I guess like did we not do it because of that? You know that also. Oh wait, it doesn't.
You will do 90-degree pulses in solid state NMR also. Because what doesn't change is the fact that the equilibrium rapidization will still be along Z. Remember, we've talked about like this discussion is about what the spatial degrees of freedom. And then there are the spin degrees of freedom. Right?
Yeah.
These are these two things are interacting with each other, but we're sort of treating them orthogonally in a sense. So the density matrix at equilibrium will still be proportional to YZ in solid state NMR. And the application of hard 90-degree pulse will still lead to mutation and the production of transverse coherence in solid state NMR also. Now, if, for example, you have a deuterium nucleus whose and you're in a solid sample, then its frequency will span hundreds of kilohertz. So you need an extremely high power 90-degree pulse, or pulse generally speaking, to be able to excite the nucleus. So generally, if you have a static sample whose frequency is spread out over a large range because of anisotropy, and you shift anisotropy, quadrupole coupling, dipole coupling, whatever it is, then you need a very high power 90-degree pulse to excite the entire frequency range. But the fundamental logic of RF pulses and their effect on magnetization, rotations of spin angular momentums around different operators, that does not change.
And then once we do the oracles, like we have to worry about like all the other terms. Basically all the other spherical harmonics in the lab frame.
No. Because
the assumption here was that IZ was like larger than IXI, right? And then once you
the induced field, if we go back to, I think I have this from the notes last time. You think about this B naught and I on the other side. Then you have the shielding tensor sitting in between. The logic here is that this, if you look at this term together, B naught sigma, that's kind of like a B induced.
okay, yeah.
And there I'm saying that the induced field, or for the induced field, only the Z component matters.
Yep.
Therefore, only the IZ term gets picked out of I. Does that make sense?
Yes.
Okay. All right. So now we have to do this rotation. We have to think about how you rotate the individual tensors to be able to get the frequency, the individual tensor number. Okay. So let's see where we have that. Okay. The L-mth component in the lab frame given by sum over M prime going from minus L to plus L. The Lm prime component in the PS frame multiplied by this rotation. Okay, so this is the general formula that you have to apply for every frame transformation. And this is what we were doing in this lecture also, where you applied this back to back from lab frame from PS frame to rotor frame to lab frame. And we are just going to walk through how to do that one rotation. So I want the 2 0 component in the lab frame, and I want only the 2 0 component. Is that right? And I want M prime to go from minus 2 to plus 2. And I know that I'm going to have effectively only 3 terms, right? I have minus 2, 0, and plus 2. So I'm just going to write out those 3 one after another. The formula says you have to have the PS component multiplied by the Wigner rotation matrix. So I'm going to start with 2 0. Okay, so this is 2 0. That's square root 3 over 2 delta times the 0 0 rotation for alpha beta. This makes sense? Remember that this D element is M prime M. M prime is the index in the PAS frame, and M is the index in the lab frame. So M will always be 0, and M prime will vary. So this is for -2, and then the same thing again for +2. Does this make sense? This is how you get the 2-0 tensor component in the lab frame by applying rotations to the individual tensor component in the PAS frame. This really is the basis for all nested rotations that you do here on. No matter how complicated a rotation gets, you have to go from molecule to crystallite to rotor to lab, and as many different frames you like. You're just doing this again and again. Okay, we're going to think about how we get this capital D element, which we saw is broken down in this fashion. Exponential, complex exponential in alpha and gamma, because those are rotations around Z. Remember? That's how we defined alpha, beta, and gamma. Where alpha and gamma are rotations around Z, beta is rotation around Y. The Z by Z rotation. And because spherical tensor components are eigenoperators of R Z, for alpha and gamma you just get out these exponential terms, whereas for beta you get the Wigner matrix element. For M prime equals 0, these two are just 1, right? M prime equals 0, I get 1 times D 0 beta times 1. That makes sense? So capital D 0 to alpha beta gamma is 1 times 1, which is perhaps at this point unsurprisingly your unless I got the sign wrong. No, I did not get the sign. So does this make sense? What does this give us? -2 to 0.
Exponential. There's the exponential term with the negative -2.
Yeah, or plus you have a minus here. Right, so it's M prime alpha and M gamma. Right, this is a very important, like a very slight notational difference, but you have to be careful. M prime with alpha and M with gamma. In other words, generally speaking, let me just write the general expression now. And because M is always 0 for my calculation, because I'm only looking at the 2-0 component in the lab frame, the gamma is going to disappear from my calculation. Does that make sense? Is this sort of like, okay, I'm going to assume that's a yes for the most part. Okay, so because here I put in -2, here I put in 0, I get e to the I0 gamma, and that's just e to the 0, which is 1. Yes.
I think I swapped after the table. Maybe it's just that way, not the other way.
Gamma being the last rotation before you of the to line up the y axis.
So it's alpha first, then beta, then gamma.
Oh, you're saying that you sort of
Like,
Right.
I don't have alpha in the final, I have gamma. So,
I'm not sure where you follow.
I just flipped in because in the bigger matrix. Maybe I read different place, so I just mixed it up, like instead of n prime the alpha, it was n prime gamma.
In this formula?
Yeah,
Oh, the slides you're saying it's the other way around.
yeah.
So that might be something that needs a correction. I have slides from a while back the 2 years ago. Was it also what we did today for NAS? I think this distinction would come up when you are doing nest rotations also. Ta-da-da-da. I see M gamma here.
Okay.
M prime alpha and M gamma. So as long as you have M gamma and M is 0, gamma dependence disappears. Something to be careful about. Of course, if you have if you're going through a nested frame, then there in that nested frame M can be anything. That intermediate frame. Then you have to consider gamma. So then gamma will show up. But in this one transformation from PAS to lab, gamma is irrelevant because M is equal to 0. Okay, so we are looking for this tensor element which is -2, 0. Right? D to -2, 0, or this small d -2, 0. M prime is -2. M prime is -2. M is 0, so that's C. C is square root 38 times squared beta. Does this make sense? That's how I picked out the -2 zeroth component in that Wigner, or the M prime equals -2 and M equals 0. So you read out that particular Wigner element, plug it in. Any questions on this? Similarly, the 2, 0 will be very similar. The only difference being you so finally M20 in the lab frame is Somebody tell me what the rotation element turned out to be. I'm not going to scroll up and down. Ask the class to tell me.
Would have 3 cosine squared data minus 1.
That was the 0, 0 rotation element.
Yeah, you know, since
Let's take 2 minus 2. So the tensor element is that, if I remember correctly.
yeah,
And the rotation element is
square root of 0 over 80.
sine squared beta. I remember. Okay.
It's less. Oh, you're good.
So 2 minus 2. Well, yeah, I can always. Right, that's 2 plus 2. Or 2, 0. Minus 2, 0, 2, 0, and 0, 0. Anybody recognize this trigonometric expression? E to the 2i alpha plus e to the minus 2i alpha. All right, any further simplification? Surely is a lot that can be done. One, I can take a lot of square root stuff. Oh, maybe not.
I think root 2. That's also,
I can also take out a half, I think.
yeah.
And what else? Leave this 2 and this 2 will cancel. Which leaves you with.
Disagrees with your answer.
Yeah, it kind of does, huh? Means one of the two places has a sign mistake. Probably the Cartesian one will be wrong. If I had to guess, because I get like I got a slightly different answer last week, and I just put the minus and then I get a plus over here, and I get a minus over here. So, and it can't be the sine of alpha because I have cosine of alpha, so it can't be a matter of the definition of alpha. And I have sine squared, so it's definitely not something about the way in which the angles are defined.
Any of these things, if you stay self-consistent, come out of the wash. But it occurs to me to ask how many of you have ever used or currently use Mathematica or MATLAB? Mathematica for these kind of closed form expressions to manipulate them and graph them or so. And I mentioned MATLAB because there's some nice NMR simulations that work make numerical recipes. Sometimes that's a way to check just for your arithmetic.
Yeah.
There's even a rudimentary free online one now that could get up to multiplying matrices of this size.
Any questions about this calculation? You can use this I mean, I hope that this has given some degree of insight into understanding rotations using spherical tensors. And if you start to get comfortable with this, you can then go home, and I would strongly encourage that you try the nested calculation that we had talked about in class today, from principal axis to rotor, and rotor to lab, and put in the correct angles, put in the right rotation matrix elements, confirm really that the MAS frequency expression that we got today is correct. Going to be extremely useful, and do it using spherical tensors in the way that we did it. So you start with a tensor by breaking it down into spherical tensor components. Consider the components in the rotated frame that you need. Calculate them one by one using the beginner elements. Rotate them again. And finally land at the 2-0 component in the lab frame. Everything eventually ends there. 2-0 component in the lab frame. No matter how many rotations you do prior to that. Yes.
Can you go over question 9?
Question 9. Yes, I was looking at my notes for that. I'm not going to spend a lot of time on it, but we just look at sort of the basics of problem 9. What does problem 9 say? Maximum dipolar splitting for an NH pair with an intermediate distance of 1.03 angstrom and what orientation of the bond vector relative to the applied field would this splitting be seen? This is also the maximum breadth of the powder broadband line shape. Okay, so before we answer that question, here's the question to the class. Given, this is some frequency, PPL. What is this likely the powder pattern of? Like let's say this is N15 and I give you a powder pattern that looks like this. What interaction is this powder pattern?
Dipolar.
Dipolar. You have one answer. The other answer?
It just looks uniaxial.
Yes, it is uniaxial. But what frequency term is it? Meaning what? Is it chemical shift anisotropy? Is it dipole coupling? Is it quadrupole coupling? Is it CSA? One says dipole and the other says CSA. You don't have many options left. Because here is where you slightly have to think about what the spin part of the Hamiltonian is doing. So this is your shielding Hamiltonian, right? Sort of, depending on how you define these symbols, you can get a slightly different language for it. But this tensor anisotropy is what is being read out here as this powder pattern. And I see this spin part of the Hamiltonian. This is for CSA. For the dipole coupling, you have in general a dipolar term, which I'm not going to. It has its kind of like 1 over r cube dependence and then dependence on the gyromagnetic ratios and yada, all of that stuff. And then it has, like that's the dipolar coupling frequency. Then similarly, you'll have a space term, which is nothing but 3 cos squared beta minus 1 over 2, where beta is the internuclear vector. What does the spin part look like?
With the
But which two components?
Yes.
Two ICSC usually for us. We sort of keep that to maintain normalization and so on. So 2ICSC is the truncated dipole handle. Right, again, I'm doing truncation of everything. If you don't commute with P naught, you go. If you anything that contributes to Z field, hold. Anything else, just go away. Right, so 2ICSZ. And ISZ, remember, can be written generally as this. Right? That's what we've been discussing. So in the absence of decoupling, what does an N15 proton dipole line shape look like?
The thing you drew about just.
So just this.
This.
Yes. Okay, so we have one answer: in phase doublet, anti-phase doublet, and I'm talking about a static dipolar line shape. You said
Like the thing you drew about with like the ends or something.
this.
Yeah, but then like double, so it's a double.
Like that? Is that what you were saying? I'm trying to guess. I'm trying to sort of take these descriptions and turn them into figures. So
It's like the in phase double, but it's like anisotropy.
right. Right. So unlike scalar coupling, which is like say I have a 100 Hz scalar coupling across the NH bond or a 92 Hz scalar coupling. And the scalar coupling, you observe it in solution because there is no dependence on orientation relative to B naught. Scalar coupling is 100 Hz no matter generally. I think okay, I don't think I would get angry if I say scalar coupling is mostly isotropic. But the dipole coupling explicitly has orientation dependence, right? This is 3 cos squared beta minus 1 over 2. Therefore, you must get an orientation dependence in your line shape. And so you get this line shape for the n, kind of like how you think of this as n plus h alpha and n plus h beta components of the scalar doublet. The dipolar doublet also has one entire line shape for n plus h alpha and an entire dipolar line shape for n plus h beta. And then what you observe is the sum of these two, which ends up looking kind of funny and hard to draw most of the time. Something kind of like that. But it's, I think, best represented as that and then that. Then you have to join all of them. Does this make sense?
So for the, you're saying it's orientation dependent
Yeah.
line shape, but does the actual position also change depending on whether orientation is perpendicular versus this is a problem? It says that there's a most shielded orientation issue.
Yeah.
Then last we were learning sigma 3 versus sigma 1 on correspondence. And at least in the CSA, diagonal.
Yeah.
They correspond to like the issue.
Yeah.
So also is like both the line shape and line length and the resonance frequency change?
Yeah, so yeah, I think I get what you're saying.
Like I was centered on isotropic shift plus sigma.
So here I'm drawing the powder line shape. So I'm literally adding signal from every single orientation relative to B naught.
Yeah.
Does this make sense? So when you take a static line shape like this one, you have every single orientation in this line shape, right? You're going from beta equals 0 to beta equals pi over 2 in this. Beta being the angular vector to z, so you go from 0, which is along the z-axis along the pole, to pi over 2, which is where you span the entire equator. The question is, which I will come to in a minute, is about like picking out one orientation from here and asking what the frequency is. But you need to be able to look at this line shape and immediately read out what like the orientations are. So like when you look at this line shape, you go, this tall edge is beta equals pi over 2, it's on the x or y. And this short edge on the other side is beta equals 0. So if I want to create a sample where I have only one in each pair, and I align it at beta equals pi over 2, instead of having a powder avalanche where I have all orientations in the southern sample, I only have one orientation of the NH relative to Z. I'll only have a signal string here. Does that make sense?
Yeah.
This line shape is explicitly because of the powder average of all orientation.
But the molecule starts to tumble in solution fast enough. This is going to collapse or weight it out. Which will be very developing. Yeah. The weights are given by these intensity and the frequency is along with that.
This is the same as what I was talking about as being a peak pattern. So you hear the term power pattern and you hear the word peak pattern. Mostly people mean this interchange.
These edges for us in solution would correspond, if you look microscopically at the shift you would see when the molecule has rotated, one of the principal axes of the shift tensor is along the z-axis.
Can you get the same thing for what it ends up
So the molecule tumbling, moving back and forth.
Ooh.
In a fake path.
Like that. That. Chris here is imagining an anti-phase dipole of that. I don't know if that has been calculated or measured ever. That's kind of how that would look.
So for some bipolar systems, you may create that
Oh, you do.
phase. You can do it for bipolar as well. But I think of a paper maybe the most.
You don't do static.
Well, it's not an unusual.
Right. Right. Okay.
Bipolar order.
Ah. So for the NH group, I have written down the frequencies for the CSA and dipole terms in this manner. I have ignored the asymmetry and so I have removed the dependence on alpha for the purposes of simplicity. And I have made one crucial assumption in this calculation, in writing these expressions. And what is that?
Uniaxial.
CSA has been assumed as uniaxial, but I've made one other assumption. In writing the frequencies for two tensors at the same time, in terms of the same angle, beta, I've made an assumption. Yeah, so the unique axis or the z-axis of the CSA dipole tensors is the same, is an assumption that we made, and I think the problem does make you do that. If I remember correctly. Yeah, it's approximately uniaxial. Alright, it doesn't, but
You can make extra assumptions. Let us assume.
okay. So, maybe you can go ahead and do a more general case when you go back. But here's an NH vector, and the z-axis of the shielding and dipole tensors is along the bond. So this is, let's say, B naught, and your NH vector has a certain angle beta, and the frequencies are given like this. So the first question should be easy to answer. What is the maximum dipolar splitting? If you put in the numbers, the dipolar coupling frequency will turn out to be around 11 kilohertz. Then what is the maximum splitting that you will see? 22. Does that make sense? Right? Because I have this edge at minus 11 kilohertz, this edge at 11 kilohertz, relative to the isotropic shift. The maximum splitting is 22 kilohertz, which is the distance between the short edge of the plus alpha component of proton up component, and then the short edge of the proton down component, an entire width. That's the maximum splitting. There is, in other words, a pair that looks like that. And for what orientation is that? Beta equals 0. Beta equals 0. Dipolar splitting. Okay, so then you have the problem goes on to ask you to consider both CSA and dipolar for this parallel orientation. Let me first assume that you have with proton decoupling. If you have proton decoupling, do you expect any contribution from the dipole coupling to the frequency? No. Right? So with proton decoupling, only the CSA term will appear. Does that make sense? This sort of like, okay, it's okay. All right. So with proton decoupling, you want the frequency in general has to be considered as the sum of the CSA and dipolar. But with decoupling, this term vanishes. And so I get just this. If I had to draw a cartoon spectrum in frequency terms, this is kind of like what the CSA powder line shape would look like if I had a powder. I have an oriented sample, and that will just give me a signal here. Does this make sense? The powder pattern in case of a sample with all orientations mixed into a powder. But for an oriented sample, where only beta equals 0, where the NH vector is held parallel to the magnetic field for all molecules in the sample, I only have the signal at delta. Is this making sense?
Why is it?
Oh, this depends on the sign of the shielding tensor. And I've just assumed that it has a. Are you confused about?
I mean, the problem gave us sample. These are like actually calculate the signs.
Ah,
I,
yeah, so delta is given as 120 ppm. Then this would land you at 120 ppm. The other end is minus 60 ppm. Which is kind of not how frequent chemical shift is written, it's flipped. And that's something that one needs to be aware of when one is looking at outer line shift. But does that make sense? Like, if you were to actually look at this frequency axis in the way that we do, you know, in terms of like ppm terms, ppm going from negative to positive in this, from right to left. Right side is negative and left side is positive, as opposed to what I've done, then it will be the other way.
okay, yeah.
But I'm just writing chemical shift going positive in the to the right side. Ultimately, this depends on the sign of delta. So there are functional groups with negative delta and functional groups with positive delta, depending on whether or not the unique axis is more deshielded or more shielded relative to the other two, X and Y. Okay, if you didn't have proton decoupling, what will happen? Another peak. So this peak and another peak.
Yeah.
Let me zoom out for a second. This is not to scale, obviously. You can tell me what that is. This where it should be? If this is where 120 ppm is where it was, with decoupling, will you expect this?
Centered on the
Right. So you should see
same things.
right. So there's going to be another peak, kind of like that. Right? You had one peak which was at the chemical shift. I don't say isotropic shift because it's not the isotropic shift, it's again 120 ppm relative to the isotropic shift. Remember, isotropic shift itself could be something like 115. So you're really looking at something which is at 200 something ppm. Right? So this is always relative to isotropic shift. Because that's how we define the components of the shielding tensor. But I have 120 relative to the isotropic shift for this orientation. Then I switch off decoupling, I split into what I call a doublet across that central position. Does that make sense? And then this splitting will be in kilohertz how much? 22. then given a static magnetic field, you can calculate what in ppm that will be. Let's say you are at 200 megahertz or 800 megahertz or whatever it is, you can convert this kilohertz number to ppm, and then you can calculate the position of these two peaks in ppm term. Does that make sense? This is how you arrive at oriented sample frequencies. And these numbers, I mean, if you were to actually put in isotropic shift and B naught and things like that, you could get frequencies as high as 300 ppm or as low as minus 150 ppm. That's not because of the chemical environment being absurd, but it's just because of the orientation being such that, and the anisotropy being so large that they either add up or subtract to give you these very large negative chemical shift numbers. Make sense? Are we all good with this?
They give you a non-zero beta. What would the outer spectrum look like in that?
I love that question. So when you have non-zero beta, can you represent the frequency in terms of one angle? No, right? It's two angles, beta and alpha. So I can't just go from position in line shape, or I mean, when I look at a position in a line shape, I kind of have only one number, which is frequency. And for a uniaxial line shape, I can go from where I am directly to beta. But when I have eta equals non-zero, you kind of have to think about just, if you want to approach it conceptually, you just have to think about the turning points heuristically, and then you really have to simulate and use powder averaging algorithms to arrive at the right frequency. So what I'm saying is, these three terms are often called the turning points of the spectrum. And let's take the case where eta equals 1. What does the tensor look like? So what do you guess the line shape looks like? A tent? Does anybody think of a tent? I think of a tent when I think of an eta equals 1. Is that, or inverted tent? Is that like that?
No.
Not sure I can imagine this the way that you are.
Okay. Never mind. Sorry.
That's kind of what it ends up looking like. But it's slightly non-intuitive. I really meant to like kind of my representation of showing you what happens as eta increases from 0 to 1. because that's what happens when eta equals 1. It becomes symmetric in frequency space. You go from minus delta to plus delta, and you have the y, v naught along y line being in the middle at 0. What happens when eta equals 1? It's, at least as far as I know, difficult to arrive at this shape purely like using analytical expressions. So mostly I've seen the handling of, I don't know if I have any thoughts on calculating eta non-zero tensor line shape analytically, but mostly I've seen this being handled using computer programs that perform bounded averaging. So try to consider all the values of alpha and beta and perform the program. Yes.
I just saw a recent paper about this, so I guess it's considered that there isn't an efficient solution. That somebody would write a paper about this, it's the surface analysis. Do you think of approaching it by particle derivatives? And it's stuck because it's not a function that you can invert.
Yeah.
In the case of Uniac, so you just work 2 segments and they're contiguous and it's okay. Don't remember what happens when you try to work this on, but they're not separable, I guess. And but somebody has just written a paper. I maybe have to find it, send it.
But the answer to your question is that it is insufficient to have only beta, then you have to specify both beta and alpha to describe an orientation of a sample. For an oriented sample, you don't just say how the energy is relative to beta, but also how does the x-axis land in the lab state. Those 2 angles are necessary to calculate the frequency contribution from the CSA. Once you've done that, this dipolar is generally uniaxial by definition and always is, unless you have other effects which we can talk about later. In the absence of those phenomena, you have uniaxial dipolar giving you a frequency contribution, and then a rhombic CSA giving you a frequency contribution, and given alpha and beta, you can calculate what the frequencies are. The problem asks you to handle the situation where beta is 0, parallel to z, so alpha becomes irrelevant in that case. So that's why I note the asymmetry saying it's not important for this problem. But that's for a special orientation where beta is 0, where it doesn't matter what alpha is. You can't define it. For other cases, you have to define an alpha. And thereby solve the problem.
As an example of an eta equals 1 molecule.
Eta equals 1, I've been thinking about that for a while. I think I may have more examples, but I think of an aromat being eta equals 1, mostly close to. Carbonyls are around 0.6. I don't remember where carboxyls.
They have something close to 8 equals 1.
Yeah.
But it depends on the hydrogen bond and the
Like. Okay, looks like the EM people are waiting to enter the room. So, hope this was helpful. Try out problems 9 and 14, and there's a very good chance that you will get stuck because we didn't talk about dynamic averaging. We will return to that in a later problem session and discuss that.
Yeah, she says